Hello, and welcome to this presentation on modern C++ compile time features. Today, we'll explore three important keywords: constexpr, consteval, and constinit. These keywords help developers move computations from runtime to compile time. The result? Faster programs, earlier error detection, and more predictable behavior. Let's dive in and learn about each one. C++ has been evolving to support more compile time computation. There are three key benefits to this approach. First, performance. When code runs at compile time, there's no runtime cost. The results are simply embedded in the binary. Second, safety. Errors are caught during compilation, not at runtime. The compiler helps verify program correctness. And third, determinism. Compile time execution is predictable. It eliminates issues like the static initialization order fiasco. By moving more logic to compile time, we create programs that are faster and more reliable. Let's start with constexpr, introduced in C++ 11. The constexpr keyword is a hint to the compiler. It suggests that a function or variable could be evaluated at compile time. But here's the key point. Constexpr does not guarantee compile time evaluation. Whether it happens at compile time or runtime depends on the context. In this example, the factorial function is marked as constexpr. If we call it with a constant expression like factorial 5, the compiler will likely evaluate it at compile time. But if we call it with a runtime value, it will be evaluated at runtime. Over the years, constexpr has become more powerful. C++ 14 allowed constexpr functions to contain loops and if statements. C++ 20 added even more capabilities. This makes constexpr useful for a wider range of problems, though it still has limitations. Now let's look at consteval, introduced in C++ 20. This creates what we call immediate functions. Unlike constexpr, consteval mandates compile time evaluation. There's no option for runtime evaluation. If the compiler can't evaluate a consteval function at compile time, it produces an error. In this example, the square function is marked as consteval. Calling it with a constant expression works fine, but calling it with a runtime variable causes a compilation error. This makes consteval ideal when compile time evaluation is essential. Think template metaprogramming or user-defined literals. The strict nature of consteval provides strong guarantees, but it also limits where you can use the function. It's a trade-off between flexibility and certainty. Also from C++ 20, we have constinit. This focuses on initialization control for variables with static or thread storage duration. It ensures that a variable is initialized at compile time. But unlike constexpr variables, constinit variables remain mutable after initialization. This is an important distinction. Constinit doesn't create a constant expression. It ensures that the initialization happens at compile time. This is particularly useful for preventing the static initialization order fiasco, or SOF. This problem occurs when global variables in different files depend on each other, and the initialization order is undefined. With constinit, we guarantee that certain global variables are initialized early, before any dynamic initialization. In our example, we declare a global counter with constinit. The counter can still be modified at runtime. This makes constinit valuable for global state that needs deterministic initialization but may change during execution. Let's compare these three features side by side. For evaluation timing, constexpr can be runtime or compile time depending on context. Consteval is always compile time, and constinit is compile time for initialization only. Regarding runtime capability, constexpr allows runtime evaluation if needed. Consteval prohibits runtime evaluation, and constinit allows runtime use after compile time initialization. For mutability, constexpr and consteval variables are implicitly constant. Once initialized, they can't be changed. In contrast, constinit variables remain mutable. This makes constinit suitable for global state that needs modification. In terms of standard availability, constexpr has been around since C++ 11. Both consteval and constinit were introduced in C++ 20, so they require more recent compilers. Each feature has its strengths. constexpr offers flexibility. The same function can work in both compile time and runtime contexts. It also provides backward compatibility, since it's been available since C++11, and it allows incremental adoption in existing code bases. Consteval provides guaranteed compile time evaluation. This ensures zero runtime cost and strong type safety. Errors are caught during compilation, not at runtime. This makes consteval valuable when performance is critical. Constinit solves the static initialization order problem. It guarantees variables are initialized early in program startup. This provides zero initialization overhead, and it allows for mutable global variables, which is useful for state that needs modification during execution. However, each feature has trade-offs. constexpr doesn't guarantee compile time evaluation. Whether it's evaluated at compile time or runtime depends on context. The rules around constexpr are complex and have evolved over different C++ standards. And debugging constexpr code can be difficult, since evaluation happens during compilation. Consteval is inflexible by design. It can't be used with runtime arguments, which limits its applicability. It only works with constant expression arguments, and it requires C++20 support, which may not be available in all environments. Constinit is limited to initialization control. It doesn't ensure that a variable is used in compile time contexts after initialization. Unlike constexpr and consteval, constinit variables are not implicitly constant. They can be modified at runtime, which might lead to bugs if constantness was expected. And constinit only applies to variables with static or thread storage duration, which limits its use cases. When deciding which feature to use, consider your specific needs. Use constexpr as your default choice for general compile time optimizations. It's ideal when you need flexibility or when code might be used in both compile time and runtime contexts. Think mathematical functions, string operations, and other computations that could benefit from compile time evaluation but might also need runtime values. Use consteval when you absolutely need guaranteed compile time evaluation. This includes template metaprogramming, user-defined literals, or when performance is critical. Consteval ensures certain calculations happen at compile time, catching errors early. Use constinit specifically for global variables where you want to prevent initialization order issues while maintaining mutability. This is important for global state that needs deterministic initialization but may need modification during execution. In general, start with constexpr for its flexibility. Only move to consteval or constinit when you have specific requirements they address. To summarize, constexpr is flexible and serves as the default choice. It allows the same code to work in both compile time and runtime contexts. Consteval is strict and guarantees compile time evaluation. It ensures zero runtime cost and stronger type safety. It's ideal when you need certain calculations performed at compile time. Constinit focuses on initialization control. It solves the static initialization order problem while allowing variables to remain mutable. It's specifically designed for global variables that need deterministic initialization. The philosophy of modern C++ encourages moving computation from runtime to compile time whenever possible. This results in programs that are faster and more reliable, as errors are caught earlier in development. For more information, check out these resources. The preference. Com documentation provides comprehensive details about each keyword, including syntax and examples. The ISO C++ standard, particularly C++20, contains the official specifications. The C++20 proposals P1073 and P1143 explain the rationale behind consteval and constinit. For a broader understanding, a tour of C++ by Bjarne Stroustrup offers an excellent overview of modern C++ features. C++ templates. The complete guide covers template metaprogramming and compile time programming in depth. The C++ core guidelines also offer recommendations on using these features effectively. These resources will help you deepen your understanding of compile time programming in modern C++.